speakers and also to the other participants. Welcome to this seminar focusing on the new opportunities provided by this huge challenge, creating an environmentally friendly aviation. But before tackling this topic, some quick administrative remarks. Please switch off your microphones and cameras so we can all clearly hear and see the speakers. And if you have any questions, write them down in the chat. We will pick them up at the end of the presentations, time permitting. Oops. Yes. Allow me quickly to introduce Agoria to those who are not familiar with our organization. Agoria is the technology federation in Belgium. Again, please, next slide. Yes, bring together more than 2,000 companies with a joint turnover of more than 132 billion euros and representing a workforce of more than 300,000 employees, making it the largest employer federation in Belgium. Agoria not only brings together companies, but all technology stakeholders in society with the aim to bring success to our members and craft not only to them, but even more to our society and our world a sustainable future. Agoria does this by providing our members individual support and advice in every corporate domain, not at least with regard to innovation. Also by advocating a favorable and sustainable business environment, taking into account all stakeholder aspirations, and finally by providing business development opportunities, including promoting sustainable products and production processes. This brings me straight to the core of this seminar, clean aviation. The aircraft platform technologies it requires and business opportunities these technologies provide. Today on our plate, 3 key topics, as you can see here, brought to you by 3 knowledgeable speakers. I leave it up to my team members to introduce each of the topics and speakers. And without any further ado, let us dive into the subject. Please remember, keep your microphones switched off and cameras also, and ask your questions over the chat. Luke, I hand over to you.
Thank you, George. Next slide, please. The Flemish Aerospace Group is an innovative cluster of about 75 members, split over educational institutes, centers of knowledge, small, medium, and large enterprises. Our ecosystem varies from niche consulting firms to tier 1 manufacturers. Our members are active in structures and systems, engines, and airport and ground support. So if you're interested in joining our business group, our contact details are on the last page of the presentation. I would like now to introduce you, next slide, please. Yeah, I would like to introduce to you Mr. Emiel Amsterdam. He's a senior scientist at the Netherlands Aerospace Center. He has extensive experience in engineering and failure analysis and is co-author of Design the Structure of the Future Aircraft. He will talk to us about structural integrity of organic structures made by metal additive manufacturing of aircraft structures as a whole. Emiel, the floor is yours.
Thank you very much. Yeah, so I will share my presentation. Good afternoon, everybody. Welcome to this talk. So I will. So I hope everybody can see the presentation. So the title of the presentation is Structural Integrity of Organic Structures Made by Additive Manufacturing and of Aircraft Structures as a whole. As most people will know, also this is our release statement. Additive manufacturing is growing in popularity, especially in aerospace. obviously because of the lightweight opportunities that it provides, and also the opportunity to create parts with added value, and those are the things that are most interesting for additive manufacturing, because we're not going to print an entire plane, as you can see here. But obviously we're going to make parts of an aircraft that have added value, and where you use the technique which is more expensive than conventional manufacturing, but you use the technique to create additional lightweight or added value to functionality to a product. However, there is only one thing that is holding back some structural or critical applications, and those are the fatigue properties. So there are some usually some pores or lack of fusion can be present in these kind of printed materials, and they lead usually to a larger variability in the fatigue life, and we'll see that later on in the presentation as well. So here you can see a pore in a fracture surface. This is a scanning electron microscope image. And here you can see a pore from which a fatigue crack started to grow. And here you can see a lack of fusion defect, which is basically caused by a large metal droplet that falls on top of the laser powder bed fusion, the powder bed. And then the laser scans over this large droplet, and it cannot melt the powder below the large droplet, and then you can create such a lack of fusion defect, and they are sites of crack initiation. So another thing to mention is that fatigue is quite stochastic by nature, and here you can see some is also a SEM image of the surface of a specimen, and we made laser defects on the surface, and you can see that cracks from some laser surface defects, cracks are growing, as you can see here for these this defect, but around this defect there isn't any crack growing. Here there's a very small crack on either side of the defect, and here's again a very large one. So it really depends on the size of the defect, the shape of the defect, and the microstructure surrounding such a defect, if a crack is fast, and if it's growing or if it's not growing. So how do we deal with fatigue in conventional design approaches? We can use save life, or we can use damage tolerance. Save life, which I think one of the first design methodologies, where you look at usually you look at crack initiation, and then if the crack has initiated, then you say, okay, then it's the end of my life of the component, and you use some kind of safety factor to ensure that the part doesn't fail in service, and from the mean life of the SN curve, you create a safe curve for the design, and you typically use smooth specimens to determine the SN curve. That's the cycles versus stress curve to design the component, and minor rules is used for variable amplitude fatigue. However, in the past, there were still fatigue failures in aerospace, and it was recognized that although there were some factors of safety, that safety was not always guaranteed. So, and already beginning of the 70s, they came up with a damage tolerance design philosophy, in where they assume that there is a flaw already present in the material and in the structure, and that it grows, and that it grows at a critical location. And they use crack growth data to determine the life, and we see that they use interaction between high cycles and low or high amplitude cycles and low amplitude cycles to deal with variable amplitude fatigue, and the safety is guaranteed by inspection. So it's also called safety by inspection. So that's the damage tolerance approach. So the one is with crack growth, and the other one deals with the Save Life deals with the crack initiation. And those two are quite separate in design of fatigue. But however, there's if we go to additive manufacturing, there are two things that are not where we cannot use a damage tolerance approach. So typically for a crack that is assumed, it's 0.05 inch, so that's about 1.27 millimeters, and it is assumed that it grows at a critical location. However, if we use additive manufacturing, we usually make complex parts with very thin walls, and we usually use shape optimization to design the part. So here you can see, assuming a crack of 1 millimeter in such a part, then you already miss some of these structures here. So that's not really a feasible assumption. Also, if you use shape optimization, for example, this is a bracket, and if there's only one load case, then you could design the part such that the stresses are the same everywhere. So by removing material that are stressed at a lower stress, so you end up with a structure that has the same maximum stress everywhere, and you have no critical location anymore. And then how do you going to use your damage tolerance approach if there is no critical location? Obviously, for application with multiple load cases, this does not hold, because you have to have material at one place for one load case and at another location for another load case. So in reality, you won't end up with a part with equal stress everywhere, but still the critical locations are not always very obvious. Where in other designs, where you have a hole or something, that it's more obvious that around the hole that's a critical location. So how do we deal with that? So that's basically the question. Which design rules should we implement in topology optimizations algorithms such that the optimized shape is damage tolerant? And here you can see an antenna. How do you basically guarantee that such a structure, if one of these connections fails, if you don't get sudden collapse of the entire structure? For example, if you look at this, you would want to have a structure which is more like the game of Jenga, instead of a house of cards, where if one member fails, that you get collapse of the entire structure. But you would like that a structure is more damage tolerant in a broader perspective, so not such that if we speak about damage tolerance, we have these characteristics of a critical location and a 1.27 millimeter assumption for a starter crack. But if you look at the broader perspective, damage tolerance is also how good is a structure dealing with damage that is inflicted or introduced in the structure. So for additive manufacturing, we would like to have a structure which is more, as you can see here for the game of Jenga, where we can introduce some damage and nothing happens to the structure. Same applies for the other structure. Here you can see a ladder structure inside, in this case, an open ladder structure inside a compressor blade as an example. How can you ensure that widespread fatigue damage isn't everywhere and then you get sudden failure by linking up of all these damage accumulation. So is this something that can happen? And here you can see an example of this in the real case structure, an aircraft structure, where there was multiple site damage, and it linked up after many pressure cycles in the cabin. Famous incident. So how can we deal with that? So to investigate that, we looked at fatigue in stretch-dominated multiple load path structures. This was a master thesis project of for a student that was at NLR. And we started with a very simple structure, because we can immediately go to very complex structure, but we can't learn that much from it. So we want to start with a simple geometry, which is stretch dominated. And if one member or one strut fails, then the structure is still stretch dominated, because all the members are in tension. So for this example, we looked at 3 different specimen geometries. One with a single strut, one specimen with 9 struts in parallel, and one with 81 struts in parallel. And they all have an equal cross-sectional area. So the force is the same. So that's what we want to investigate. How good is the structure in maintaining that force over a long period of cycles? And they also have equal surface area. As I mentioned before, fatigue is a stochastic process. So it also usually the fatigue cracks start at the surface, and especially for additive manufacturing, they start at the surface. And if you have more surface, there is more possibilities for cracks to initiate. So fatigue life is also a function of the area, the surface area of a specimen. So in these 3 specimens types, we kept those 2 the same, so the cross-sectional area and the surface area. And that's why these specimens with the 81 struts are less long than the single strut specimen. So we tested these in fatigue, and these are the results. So here you can see the normalized cycles to failure. So we normalized all the results by the average of the single struts at 140 megapascal maximum stress. And these are the results: the number of cycles to failure on the vertical and the maximum stress on the horizontal axis. And here you can see as the maximum stress increases, the number of cycles to failure go down as expected. But these are the results for the single struts, and we see that the results for the 9 struts specimens are decreasing, and that's quite a remarkable result. So that the life, if we increase the number of struts, that the life decreases, and if we go to 81 struts, it even increases more. While the load on all the specimens and the cross-sectional area is the same as I mentioned before. So that's remarkable. Here you can also see that for the single strut specimens, 3 results are almost the same here, but they see some scatter. So occasionally there is one specimen with a extra low life. So it's also typical for fatigue, and especially for fatigue of additive manufactured materials, where you can have occasionally a large defect in the specimen or in the material. So that's the 2 things that we can see right away. So to investigate if the life increases with the number of struts or if it's effect of the diameter, what we did with the 9 strut specimen, we took one 9 strut specimen and we removed the individual struts from this 9 strut geometry. and we tested those as single struts. So then instead of the one strut geometry with these have a 9 mm diameter, we use also single struts from the 9 strut geometry, and they have a diameter of 3 mm. And here you can see the result. So if we take the individual members of a 9 strut specimens, here you can see the scatter. So there's a larger scatter, and we can conclude that the decrease in life is really due to the decrease in diameter. So here you can see these single struts have a diameter of 9 mm, and these ones have a diameter of 3 mm. So the decrease in life is due to the decrease in diameter. So that's a remarkable result, and we will investigate that further. What's also which can be noticed is that the average life of the redundant structure, so that's the 9 strut specimen, is slightly lower than the average of the single struts, and the scatter is lower. And that's also something that you would expect. So in the 9 strut geometry, if one strut fails early, then the entire specimen doesn't fail yet, but the load on the 8 remaining members is increased, and with that increased load, the fatigue life decreases. So it is expected that the fatigue life of the 9 strut geometry is slightly lower than the average of the individual members, but also the scatter decreases due to this load sharing idea. So this is what we would expect if we use a redundant structure, that the scatter is much less because the load is shared once one member is failing. So this is already a good result, but we still have the difference in life between the different diameters. So that's something that we have to investigate further. So this is done in a project which starts in September by another student, and he will investigate the origin of the size effects for additive manufactured materials and conventional materials. And we use other alloys, and we use complexer structures, so that in the end we have some design rules which would guarantee such a structure as this antenna, that it's damage tolerant. So if, for example, this very small strut is missing, that it does not lead to direct failure of the entire structure. So that's also what we, for the additive manufacturing and components, those things of damage tolerance and how do you sign it. It's also a similar topic for the aircraft structure as a whole, because in the future we expect that the structure will be more organic, and we use also shape optimization software for those entire structures. So it's basically a similar problem, but on a large scale. So we have some factors that are also influencing the damage tolerance philosophy for large scale structures. One of those is indeed the introduction of additive manufacturing, of new production techniques. The other one is the increased use of optimization tools, and you can see that also in the EU calls. The push to circularity, both on resources, materials, but also on CO2 emissions. And there is still a push to lighter aircraft structures. That's also seen in the clean aviation Srira. So to incorporate optimization tools and to use integrated design and manufacturability, to apply that in the design tools, we see a need for a clean sheet holistic structural design and integrity approach, and I will explain what we mean by that. So we wrote a white paper on this, on that we see our ambition and our the need for this clean sheet holistic design approach, and we made a white paper on that, and you can see it on our website. We published it last month, and it basically says if you want to use a holistic multi-criteria design approach, you can optimize things. Obviously, you want to optimize performance, passenger comfort, all these kind of things, but also manufacturability, repairability, recyclability, environmental impact. You want to look at costs for manufacturing or ownership, total cost. But in all these cases, you have to account for time-dependent degradation mechanisms, and one of those is fatigue initiation and crack growth. So that's the structural integrity part of that. And we want to introduce a single fatigue design philosophy for structural integrity. As I mentioned before, the two are now separated. We still have save life for crack initiation and crack growth for the damage tolerance, and we think that is two pieces of the same medallion. So we should have really one single fatigue design philosophy for structural integrity. And some of these design tools that we are using are still from the 60s and 70s, where we have little aid from computer calculations or simulations. And we also showed that structural risk analysis of single and multiple load path structures showed significant conservatism in the current damage tolerance design methodology. So we think that by introducing a single fatigue design philosophy that's based on physics and probabilistics, and acknowledged the initial discontinuity state distribution, so that basically the defects or which are rogue flaws or other things inside the structure, that we can use that to determine the life and the structural integrity of the aircraft. And this gives a more benefit from the strict quality assurance systems that are imparted at many companies and factories. And we could use information that is gathered afterwards. So during the life, we also collect information about the structure, but we don't always use that information. So if you use a probabilistic approach and you do inspections, you can use that information to verify your initial discontinuity state distribution. So that's something that we think is useful, and we could transition to a structural risk analysis. Now we use a lot of safety factors, but we don't quantify the risk. We just assume that the factor of safety is sufficient, and it's also historically proven that it's sufficient in most cases, but sometimes we still see cracks in our structure, and there is a need for repair, or parts fail or something like that. So it's not always safe, though the factor of safety is not always sufficient. So if you assess the risks, then you can reduce the factor of safety and still maintain the current level of safety. Look at the time. So basically what we propose in the white paper is that if you go to virtual testing and you have a certain level of confidence in your virtual test, then you're still testing probably some part of the structure, and you also in the virtual test also model the test rig as well. But if you extend that, basically you still have load introduction points to your structure in a virtual test, but basically you want to extend that to the entire aircraft structure and have aerodynamic loads imposed, and then you transition from a virtual test to a virtual surface life test, and where you also use the actual the flow over the aircraft to calculate the deflections of the wings and all these kind of things to determine the loads in the aircraft. So basically, if you then combine the virtual surface life test with your structural risk analysis, you will get a failure distribution or chance of failure for all your failure modes. So that's both static and fatigue, and you can incorporate creep and corrosion as well. And if you then close the loop between the design and the virtual service life test, then you can design something and immediately evaluate the life of the entire structure. And by closing that loop, you can optimize the entire structure. So that's something that we propose, but that's a long way into the future because it probably takes a lot of calculation power. So we'll go to the next slide. And once the aircraft is taken into service, obviously you want to keep track of all the loads as well and compare that with the original design as done today. And there the digital twin is really a tool where you have the digital threads, which is the information that is gathered about different things such as the weather, the speed, all these kind of things. And you have your degradation models, and those two combined will give you the physical state of the structure, which should be then a real digital twin of the physical entity. And as I mentioned, you can use the inspections that is done on the aircraft. You can use that to check your initial assumptions if for the presence of defects or rogue flaws in the structure. And you can then also apply predictive maintenance based on these digital twin calculations. So for material selection and development, we see that if you use such a design approach, that it will in the end result in some kind of hybrid structure. Where metals are used at places where they are best, and then composite materials are used at another place where they are the best choice of material. So for metals, we still see that there is a lack of relationships between the mechanical properties and fatigue crack growth. Because, for example, when you look at fatigue crack growth of annealed materials, if you look at aluminum annealed, then the crack growth rate is exactly the same as for a T7 heat treatment. Where you see the difference is for crack initiations. There's the difference. But if you apply a damage tolerance kind of approach, and you already assume a flaw or a crack of 1.27 millimeters, then you only have crack growth, and you can choose between annealed material and T7 material. And obviously, in reality, T7 is used because those typical flaws are usually not there, and you have the benefit from the high strength of the material. But the physical relationships between these properties, so the mechanical property, the tensile stress or the tensile strength, crack initiation, fatigue, and crack growth, they are not really there. So that's something that we want to work on. And also replace alloys which contain critical materials based on these physical relationships. If we understand it better, we could make different alloys, and also incorporate residual stress technique for fatigue enhancements. I'll skip the composites for just a second because of the time. So yeah, so all these things that we want to or we want the single fatigue approach, we want to investigate that further in our Prof 2 project, which will take off in next month with the partners that are indicated below. So Constellium, Kai, Ruach, Airbus, Lagerwey, which is a wind turbine manufacturer, and Fokker. and the total budget is about 1 million euros, and the cash contribution of the individual partners is 15k per year. So we still have the opportunity for companies to join up to next year. And as I mentioned, we will investigate these relationships between the mechanical properties, the static ones, and the fatigue life and the crack growth, to really have better design rules for metals, and then also for variable amplitude fatigue, and should be physics based and applicable to multiple alloy systems. So that's it.
Thank you, Mr. Amsterdam, for this very insightful presentation. I see there are a couple of questions in the chat. We have to make it a bit quick, but
Yeah.
I will run through them. I will start with a question from Mr. Bertin. He says that, okay, don't you fear to end up with composites in the sense that you present metal that afford cracks, and you have a multi-load pad, then you go to many thin load pads, which correspond to fibers, carbon fibers, and in the end, these are composites.
Yeah, you can. If you look at the lattice structure, you can see it as a composite of made of air and metals. But still, metals have different, and also metal stochastic metal structures, or metal foam structures, have different properties due to the presence of ductility. So you should really deal with them differently, but in the limits, you can consider them as a composite material in the end. Yeah.
Okay. So then a second question, which is coming from myself, when I was seeing the results from the fatigue life testing with the multiple struts compared to the single strut, you see, okay, that the number of cycles is going down with the number of struts, but it also looks like the variation is less. Is this simply an effect of the fact that the number is lower, and so you don't see the variation, that it breaks or works one time, or is it an actual effect that you can imagine that due to the several struts that the failure will be less impactful upon the first failure?
Yeah, so that's the idea. So with the redundant structure, it is more damage tolerant. So you can inflict some damage if one of the members, one of the struts fails quickly, then all the other will take over and share the load, which will reduce their life of the total. But there is less scatter because of the shared load. Yeah. So it's more damage tolerant. So then that was the initial idea. Can we use it to have to make a damage tolerant structure?
Mm-hmm. And then a last question from colleague George. George, if the push to lightweight materials to lightweight leads to organic AM structures, but this in turn leads to increased fatigue risk, does this mean that we need to increase inspection rates? So in the end, have a higher cost on lifetime.
So in the end, we don't want an increased fatigue risk. So we would like to design something that is as safe as current structure, or even safer. And also inspection of these parts can be quite difficult. As example was this blade with the internal structure. It's very difficult to inspect these. So other inspection techniques must be explored as well. Maybe something like resonance testing, where you excite a part and look at the stiffness matrix of such a part, and if the part is not perfect, then it will have a different stiffness, and you can measure that. So these kind of things could be used to check if a structure is good. But we have to ensure that we can probably decrease the risk of fatigue if we design them right.
Okay, thank you very much again, Mr. Amsterdam.
You're welcome.
So, like this, we arrived at the second part of the webinar for today. So also good afternoon from my side. My name is Kevin Poelmans. I am a business group leader for Agoria Composites. In this second part, we will talk about the opportunities that this trend towards a clean aviation also brings to the composites industry. Currently, Agoria Composites has 50 member companies. But if you look at the Belgian industry, there are about 200 companies active in the sector. And these are offering about 6,000 jobs to people. And the sector revenue is about 1.6 billion euro. As Agoria is a trade federation representing the technology sector, we have the advantage that we have also the market sectors for the composites under the same roof. You can imagine the aerospace, like for today, building technologies, energy, machine components, and so on. Of course, as we are part of Agoria, we adhere to the overall Agoria vision, as George already stated very clearly in the beginning. And so if we take a look at, I hope you can still hear me because I'm sorry.
No, it is okay, Kevin.
All right. For Agoria Composites, we believe that a closer collaboration between national and international stakeholders is really necessary. And so we strive to represent then the Belgian stakeholders on a national level, but also on a European level, because we are also embedded within the umbrella structure of UCIA, the European Composites Industry Association. We want to act as the unified voice for this sector. And for this, we gather, in fact, the necessary information and share it with our members. And we try to make sure that the activities that are organized around composites are streamlined. The fact that we are here today in a webinar joined by 4 business groups is a very nice example on how we strive to facilitate the connections between technology and market. Of course, this is all with a higher goal to drive growth and business development. Now I have the pleasure to introduce the next speaker, which will be Mr. Tim Frerich. He started his studies in Aachen, where he obtained a bachelor degree in aerospace engineering. After this, he continued his studies in Bremen, where he got this master in production engineering. He decided to stay in Bremen after this and acquire a PhD at the Faser Institute, but left a bit earlier to join the CTC, so which is in Stade, who is a 100% daughter company of Airbus Operations. And it's also a technology center, of course, for lightweight construction with a focus on composite materials. In this role, he works as a project leader in the field of cabin and airframe structures. So besides his role on simulation topics, he's also taking on the coordination of hydrogen topics together with his colleague, Mr. Tobias Renke. During this presentation, he will share his thoughts of the CTC on the opportunities that there are for composite materials in this emerging field of sustainable aviation. Mr. Frerich, the floor is all yours.
Thank you very much, Kevin, for this nice introduction, and also for the invitation and the possibility to share our thoughts on this topic. Can everyone see my presentation?
Yes, we can.
Thank you very much. Okay, so I want to talk about sustainable aviation today and the opportunities for composite structures in this emerging sustainable aviation. Before I go into that topic, I just want to very briefly, just 2 slides, introduce what the CTC is. CTC, as you already mentioned, is 100% subsidiary of Airbus Operations. We have more than 50 employees, of which 35 are engineers, and additionally more than 25 students occupied at the CTC, working on lightweight structures with, of course, a focus on composites. We're not just doing engineering, but additional to this, we also have a shop floor, 2,500 square meters, fully air conditioned, where we can produce parts and do experiments. We are integrated in the Airbus technology programs, but we also cooperate with suppliers and other development partners also outside of the aviation industry, everything where composites are applied. We offer services in 4 business fields. The first is innovation, where we do research and development of new structures and new technologies. The second is our field we call solution, in which we transfer those developments into industrial solutions for our clients. The third field is our production. As I said, we have our own shop floor and do prototype and small series productions for all kinds of applications in the fiber reinforced plastics world. And our newest and most recent addition is the business field of education, where we offer trainings for our customers to make them ready for processing composites and designing composite parts. In the field of innovation, where I'm situated, we have occupied ourselves with sustainable aviation and how composites, what opportunities for composites arise in this field. And I would like to share now the thoughts of us on this. As a short introduction, I would like to talk generally about what kinds of sustainable aviation are possible. And we see there's 3 options. The first is battery electrics, the second hydrogen, and the third sustainable aviation fuels. For battery electric flight, this offers a CO2 or emission reduction potential of 100% if clean electricity is used. But this is only applicable to very short range flight, so urban air mobility, basically, because the energy density of the batteries is low and cannot be used as for longer ranges. There the weight of the aircraft would increase too much to have anything feasible. So the second option is hydrogen, and I said here liquid hydrogen, because while hydrogen has a 2.8 times higher energy density per mass than kerosene, in the liquid form it just has 25% of the energy, 25% of the energy of kerosene per volume. So it takes 4 times the volume as a comparable kerosene tank. And in gaseous forms with pressurized tanks, this is even bigger, so it takes even more volume. Therefore, it might be applicable for short range flight, but for everything longer, it's not really applicable. I will talk about the application on long range a little later on. With this hydrogen technology, there are options to burn the hydrogen in fuel turbines. Then we save roughly 50 to 75 of the emission, or the option to use it in a fuel cell and use the generated electricity for electric motors. Then we can save 75 to 90% of the emissions. And the hydrogen with the cryogenic tanks required offers, of course, interesting new structural opportunities for composites. I will go in depth about this. The third option are sustainable aviation fuels, either based on biomass or as a second option based on hydrogen, which is then processed with carbon sourced directly from the atmosphere. This also prevents CO2 emissions because the same CO2 that is emitted later on is first taken out of the atmosphere. There are some other effects on the climate with the soot and the NOx aviation. So the possible reduction of the CO2 equivalent is just 30 to 60%. The big advantage of the sustainable aviation fuels is that they are drop-in fuels. So there is virtually no change to the aircraft required, at least in comparison to hydrogen. And they can just be used in conventional aircraft right now. So I will not focus on them as much because there's not so much change in the aircraft. There's just one remark. Those sustainable aviation fuels can be expected to be more expensive than kerosene. So one opportunity for composites here is this creates a bigger push to a more lightweight design where more opportunities for composites rise. But I will now focus a little bit more on battery electric and liquid hydrogen flight, and I will go through the market segments with from low range urban air mobility to the long range. So urban air mobility, I've shown here the most important characteristics to understand the opportunities for composite structures. On this city Airbus, I used this aircraft of our mother company, but this is applies basically to most urban air mobility aircraft. And one characteristic is that they use vertical takeoff and landing, which is a must to operate an aircraft in an urban environment. And the second is that they use electric engine with batteries, and some concepts use hydrogen and the fuel cell to extend the range. The vertical takeoff and landing offers interesting opportunities for composites because in contrast to a fixed wing aircraft, the complete weight has to be overcome by thrust. And so the impact of weight on the fuel consumption in this vertical takeoff and landing stage is much higher, and there's a very big push for lightweight designs. Furthermore, these lightweight designs can be applied virtually everywhere in the aircraft. The electric engine is not as warm as a combustion engine. The spools, the copper spools maybe get some heat, but overall CFRP can be used in nearly every part. So this is seen by virtually every urban air mobility producer or a company right now. One important aspect which we at the CTC think not everyone is considering is these aircraft which with a passenger capacity for 4 passengers, there are substantial numbers of aircraft needed to influence mobility significantly. And so these structures have to be ready for really an industrial production and industrial composite production. And this has to be considered early on in the design. It is something we at the CTC focus on in this urban air mobility segment to help our customers to achieve industrial producible structures. So if we increase now the range a little bit and go to something like a regional aircraft, there, as I previously said, batteries are no longer an option because the energy density is too low, and there hydrogen will have to be used for sustainable aviation. An aircraft might look like this with hydrogen. To the kerosene tank. Sorry. In contrast to the kerosene tank, which is an integral tank, which basically means there is no tank. The wing structure is a tank. Cryogenic tanks with minus 253 degrees Celsius need insulation and a dedicated tank structure, and this increases the weight of the aircraft. This creates, of course, opportunities for CFRP. Have other structures in the aircraft which are currently produced out of metal. For example, in regional aircraft, the fuselage is often metal, can be substituted for CFRP to compensate the weight, or the tank itself can be made out of CFRP to reduce the weight. While for regional aircraft, as shown here, this is not strictly needed because here one can live with a relatively heavy tank. But if the range increases, the lightweight requirements on the tank increase because it's easy to imagine the tank is carried over so the tank structure is carried over a longer range. This can be shown with the gravimetric index, which shows the percentage of fuel mass on the total system mass. And here is the required gravimetric index for several aircraft is shown. We can see this increases drastically from short-range commuter or regional aircraft to short-range, medium-range, and long-range aircraft. And in these aircraft, composite tanks we think will be necessary to store the cryogenic hydrogen. There are, of course, no cryogenic hydrogen tanks for aircraft yet. So to identify specific problems, challenges, and also the opportunities it presents, how much weight can be saved, we at the CTC did a look at the space industry. And the first tank that we know of, the large-scale tank that we know of, this one is 2.5 meters in diameter and 4.8 meters in length, has been developed by McDonnell Douglas in 1987 for the DCXA Delta Clipper, which was never produced, but the tank was produced as a prototype. There's not terribly much information available about this tank, just that it was made out of prepreg and that it was successfully tested in ground and flight test. So this shows that it's in principle feasible to have a CFRP tank. Another tank was produced by Lockheed Martin for the X-33. This is also 8.5 meters long and 6 meters wide, so it's also of substantial size. And here a sandwich construction was used with an inner tank top face for the tank and an outer tank, and between them honeycombs to act as a stiffener and also as a thermal insulation barrier. And during testing, what happened here is that the excessive temperature difference of minus 253 degrees Celsius caused different thermal expansion in the fiber and the matrix material, which caused micro cracks to happen in this inner phase sheet. This allowed the hydrogen to permeate through, collect in the honeycomb core, where it evaporated, the pressure increased, and the top phase delaminated, and the tank was destroyed. This indicates one of the major problems of composite cryogenic tanks. This is the occurrence of microcracks in the tank structure, which allows hydrogen to permeate. Based on these results, in 2004, Northrop Grumman built another prototype of a CFRP hydrogen tank for the Space Launch Initiative program. And here, 3 innovations were used. One was that thinner carbon plies were used. This helps reduce the number of microcracks. I will come to this thinner ply topic a little bit later on again. Another thing that was done was to introduce an aluminum foil between the inner skin and the honeycombs core as a barrier for hydrogen permeation. And the honeycomb core was subjected to vacuum to suck out any permeating hydrogen. These tanks were successful in testing, where after 40 filling cycles, the tank still maintained its structural integrity. 40 filling cycles is something that also indicates one major difference between the aircraft tanks and the space tanks, because while for space 40 filling and draining cycles with liquid hydrogen are perfectly enough, For an aircraft, this is of course way below the number that is required. There's thousands of filling cycles have to be endured by the tank, which has to be considered in aircraft CFRP tanks. A next tank was produced in 2011, or from 2011 to 2014. In the CCTD program, Boeing, Northrop Grumman, and Lockheed Martin all subjected designs for a liquid hydrogen tank made of composite materials, and the design by Boeing was chosen, and the tank was produced. This was made with toughened out-of-autoclave prepreg, also with thin plies to prevent microcracking, a vacuum insulation around the tank, and it was found in testing that the thin plies prevented the microcracking, but the permeability was still too high because the porosity of the material, due to the out-of-autoclave manufacturing, allowed too much permeation. More permeation than specified in the requirements. So one thing here is that the production is also an important production process. Curing process is also an important thing to produce a CFRP liquid hydrogen tanks. So all these previously discussed tanks were in the US, but there has also been some development in Europe. And in the Advanced Cryotank Research Project CHAT in Europe from 2012 to 2015, composite liquid hydrogen tanks were investigated. 4 tanks were created here, 1 cylindric with liner, 1 cylindric without liner, and complex tanks with liner, and a dry wound tank without liner. The result was that the TRL was assessed to be between 3 and 4, and that was also noted in the report that Europe is lagging behind of the US in this topic of composite hydrogen tanks or composite cryogenic tanks. The most recent development here, started in 2020, was the Ariane 6 black upper stage with cryogenic hydrogen and oxygen tanks. We discussed here with people involved in this project and came to the conclusion that roughly 40% of the requirements between space and aircraft industry are the same, and that there is a lot of synergy which we want to use working together with the people from the space industry in creating a CFRP cryotank. So to sum up this overview of the history of CFRP cryotanks, there are great opportunities. All these tanks show that the weight compared to an aluminum lithium tank can be reduced by 20 to 40%, which is of course a lot, and allows this, as I've previously shown, the weight savings in the tank area, which are required for longer range, or short and medium range hydrogen aircraft. Another opportunity here is quite untypical for CFRP structures, that they are cheaper to produce, or cheaper than metallic structures. Here, because for the CFRP materials, very efficient production technologies can be used. For example, winding processes, which are highly automatic and can produce basically the complete tank structure in one part. But as I hope I've made clear, there are also significant challenges we have to overcome. First of all, the TRL for CFRP tanks, so the technical readiness level, is definitely lower than for metallic tanks, and there's development needed. One of the major issues is the H2 permeability by microcracks, also by manufacturing process imperfections that has to be solved. One challenge is the the fatigue behavior, with the much highest number of load cycles compared to the space industry. Then, of course, impact behavior is a topic. Impact behavior is always a topic with CFRP. but the material gets more brittle as we cool it down to minus 253 degrees Celsius. So that's an important topic. The insulation is, of course, a topic which has to be investigated, which can be solved, but it is a challenge. And last but not least, certification and testing needs to be developed. But this is also true for the metallic tanks. There is just no certification and testing procedures for aircraft liquid hydrogen tanks. We at the CTC have identified two technologies which we think are have a great, promising to overcome these challenges. And I would like to present them very briefly. One is the Synply technology, which is indicated here and which I referenced earlier. Synply technology basically uses one effect. If you load a regular ply, here indicated in brown, statically, then it fails at this point, but first delaminations and microcracks can be observed way before this. And if you decrease the size here by half, here by 3, and here by 6, microcracks, so the area where microcracks occur, moves much closer to the failure strain. You can see this also here. Those structures have the so combined the same number of fibers in the same directions, but here all in thin plies and here in thick plies, and they have been subjected to the same loads. You can see here that there are no cracks yet in the thin ply structure, and a lot of cracks in the thick ply structure. And the same occurs also for fatigue. No fatigue-induced cracks visible in the thin ply structure. A lot of cracks in the thick ply structure. So we think that this is a key technology, and it's also been shown in the past that this helps with the microcrack problem. It can be used in laminates where thick plies are combined with thin plies that get this effect, because of course here layup times are increased if you decrease the thickness of the plies. The second technology we at the CTC want to pursue is thermoplastic materials. There have been investigations that at this minus 253 degrees Celsius, PEEK has a much higher failure strain compared to epoxy resin. We see here 3 times. And also used in laminates, here with the cross-ply laminate, PEEK has a much higher failure strain. And this helps with the creation of micro cracks due to the CTE mismatch of fibers and resin, and also with the impact behavior. We can see here a trial where a PEEK specimen was subjected to a cryogenic hydrogen, and after 100 cycles of subjecting it to it, there was not crack yet, observable in the peaks there yet. So this indicates that semicrystalline polymers are a very promising technology. Maybe not a PEEK, but we have no material data for other materials yet, but we want to investigate that. And it is, of course, combinable with the Synply technique. And that's an approach we want to pursue to get tanks which are capable to fulfill the requirement of aircraft. So with these tanks, the range from commuter to medium range can be fulfilled. If we look now into the long range, of course, their tanks can be built with composites which will make such an aircraft technically feasible. But we can see here the costs of preventing CO2 emissions for hydrogen for these different aircraft or aircraft types compared to the cost with syn fuel. And we can see here very clearly that while from up to the medium range, there is a business case for hydrogen aircraft. If we use get these tanks to the gravimetric index we specified earlier. But for the long range with the design with tube and wings, the conventional design, there is most likely no business case for a hydrogen aircraft. To get the higher CO2 emission abatement possible with hydrogen, here more revolutionary designs might be promising. So, for example, such a blended wing body or a flying V shape, and of course, with such revolutionary shapes, we can see it here, that there are big opportunities expected in the further away future also for CFRP structures in this aircraft. So this concludes my presentation. I've taken slightly too long, I'm sorry for that. But I'm happy to answer your questions. And if you want to contact me, please, it's also possible per email. So thank you for allowing me to present our ideas here.
Thank you very much, Tim. We're indeed running out of time, but maybe one question coming from Wouter Wienand. Could the use of engineered thermoplastic composites decrease the risks of mini cracks compared to epoxy-based prepregs?
Yes, we think so. Exactly our thought that this decreases the risk of micro cracks drastically, especially when compared to the thin ply, combined with the thin ply technology. So thermoplastic thin plies, we think that this is a very promising technology.
Okay, we have to go to the next presentation. So thanks again, Tim, for this interesting presentation. Your contact details are known, so you might be contacted by one of the members who are attending. Thank you. This brings me to a very, very quick introduction of the business group of Agoria, which is the business group Additive Manufacturing. I'm the business group leader of that group. You see on the picture on the right, you see all the companies in Belgium that are Agoria member and active in the field of AM, so that's quite a bit. They're not all plotted there, but what we try to do in this business group is informing our members in different ways. So members, non-AM members or AM members. So connecting all these members, trying to help understanding the AM technology better and supporting business development opportunities for our members and defending the interest of AM on a Belgian and European level. That brings me to the next slide and to the presentation of Mr. Volker Robrecht. Mr. Volker Robrecht, he's educated as a mechanical engineer with specialty in lightweight engineering and composites. And today working at Airbus as an airframe structure expert. He will be explaining us some very hands-on experiences with additive manufacturing at Airbus. So Volker, the floor is yours. Good luck. We see the presentation, we don't hear you.
Sorry, this was double muted. Huh?
Okay.
Thank you. Thanks, Sven, for your introduction. So good afternoon. So I will give you some insights of additive manufacturing, where we are at Airbus, especially also with the context of clean aviation. So the presentation is mainly focusing on Airbus commercial. So I'm not looking too much in defense and space applications, which is a different field with different materials, as well, not on helicopter too much. So as an introduction, so the motivation is as commonly known. So the majority of parts which we implement is just simply pure based on reduced cost. So we have also a couple of parts which we are using for agility motivation. So at the end, this is lead time, which is important not only for serial production, but as well for sure for after sales business, where it is even more a driver. So we're using it as well for product performance. At the end, product performance for us, at least for the parts which we're going to use, is mainly weight. So reduced weight. So we're not using it that much for systems where we get, I would say, a better performance of the system itself. So how are we going to introduce the parts? So, Emil has already given some insights on critical and non-critical applications. So we start very simple with non-critical parts. So this is at the end a lot parts static stress based on are much higher than fatigue loads, so that we will never run into a fatigue critical case. And more we are exploring and also certifying fatigue critical parts. So we're using existing materials, which are also known on our side. And then for sure we want to deep dive in also in new materials. For the designers, so we're using still of ISO designs, just simply because we have the opportunity to compare the behavior. And then for sure we are doing also design for manufacturing, where we're sometimes also, I would say, relatively advanced. The implementation itself, so we start with running programs. So this is an important step towards, with respect to authorities, so EASA and FAA, just simply to demonstrate, not only for them, but as well as for us, that we experience on several applications, to be sure that we are in a good position when a new program will be launched, that we have something to start on. So technology scope, so starting with polymer techniques, so we are using filament technology quite a lot with the Ultem material, so which is a PEI mixed with a polycarbonate. We're using also SLS technology, mainly with the PI12 powder, as well as with a PEC powder, carbon fiber reinforced. So for metal technology, we are using powder bed technology, mainly with titanium materials, as well as nickel chrome alloys, or also known as Inconel materials. And we're using direct energy deposition materials or processes with the filament technology, as well with the powder. So when we look for metal, so I will start with the powder bed technology first. So we are using this kind of technology for our, I would say, most complex geometries. So where we are also implementing the most advanced designs. And at the end, we are looking here for weight clearly and also cost focus. So picture what you see on the right is as a double-walled fuel pipe. So which we are using sometimes on certain areas in the aircraft, and which is a good example of application with respect to complexity. So the opposite is the direct energy deposition process with a filament. So at the end, this is a very simple geometry. So the parts are usually either they are forged parts or they are very simple machined parts. So what you see here is a pylon spar. And we are using a one-to-one replacement of the design, and this is purely motivated by cost. So there are no benefits in terms of weight. It's just simply cost. And then, as I would say, the mixture of technology is laser metal deposition. which is at the end also DED technology, but with the powder, and we are using this for a medium complex geometry. So, for example, pipe couplings, which usually do not make sense with the other technologies itself. So, and we are developing this together with our colleagues from PFW, Pfälzische Flugzeugwerke. So also there we're starting with one-to-one replacement, and also here the focus is on cost, as we are using there quite sometimes welded parts, machined parts. So usually they are relatively cost intensive as well. So focus on polymer. So we start with our first application area. So this is customized cabin. Airline. As well, we have some customized area which are close to the door entrance, and we're using it also for after sale configurations. So for these kind of cabin applications, we are using filament indeed. And nevertheless, so this requires quite a lot of post-processing efforts. So they have to be visually very perfect, and this requires a lot of manual work. So it's not, I would say, still not the perfect technology, and we are more and more using as well powder bed technology for this kind of application, mainly then with the PEG material, just simply because the FST, so the fire, smoke, and toxicity behavior is much better. So our second big application area is system installation. So that means at the end pipes. So medium to small sized pipes. So our large pipes, which can be done by polymer, usually are out of composite. So this is nothing where we can compete with the cost maybe, but not with the weight. So we're using it a little bit on air conditioning then. So we're using it as well for system attachments, so brackets for electrical systems or something similar, quite a lot. And for that as well, we are using both the filament technology as well as the powder bed technology. So after sales, as I mentioned already, is quite an interesting field for this. So the lead time is really a key topic there. So the usually working parties are very short in time, and so therefore the additive manufacturing is still a good opportunity to use. Nevertheless, also it shows there that it depends really on the application and also on the possibilities of conventional technologies. So a lot of conventional technologies are also very fast, and especially because people are experienced with that. So the less experienced people are with the technology, the longer it takes. So it's still a little bit tricky. Nevertheless, we have a couple of interesting and good applications for the after sales, and we are looking also to grow this field of application. For sure, a second motivation there is also the cost. Conventional technologies, especially when they are fast, they have their price. So therefore, also additive manufacturing is a good application. And we do also a little bit of these kind of weight saving parts, but not that much, because the effort is usually very, very high. And as it is our after-sale market, we are not doing super high modifications, at least not for these where additive manufacturing is interesting. At the end, the weight saving does not count. So it's really a really minor effect. So where we are with additive with respect to our environmental footprint. So we have mainly two aspects. So one is related to the component itself, and the second one is related to toolings. So for the component itself, so clearly weight is an important factor to get operational, I would say, effort and energy reduced. And we're using, therefore, optimized design. Nevertheless, so we are not using it that intensively, because when you experience in optimizing that kind of solutions, so the development, certification, testing, etc., is really a high effort. So it has to make really sense. So when you have really a high weight saving, that this kind of high effort in development is really going in to show global benefits. So clearly for this, we have also less raw material. Nevertheless, raw material as well is related quite a lot on recycling rates. So this is also the same for conventional materials and technologies. So we have to consider always the recycling possibilities for materials when we see this as a big environmental impact. A third point is the energy consumption. So the additive printer, usually they require high energy consumption. So not only the process itself, also the post-process, especially when we're looking to minimize pores and so on. So where we're using a HIP process, high isostatic pressure, which we know from the casting, which is classically in casting used. As well as in the material manufacturing. So the powder manufacturing as well, especially in the high quality what we are using, is also relatively require a lot of energy at the end. So when we're looking for toolings, so a clear driver is that we avoid toolings as such. So that means just simply all the process related stuff and also the material itself. And we're using it for high customized cabin parts. So that means usually in classical technology, so either it is composite or sandwich, you are generating a tooling dedicated to one airline, and then you generate a part. So you see here so-called curtain header, which we developed together with our colleagues from DL Aviation. So these are perfect parts for it to reduce tooling, and this is at the end not only good for the environment, but it's also good for the cost itself and also for the lead time, as we can reduce it by half approximately, just simply by avoiding tooling.
So sorry, Volker.
Yes.
Yes, your slide is not moving. We're still on the slide where you have the focus on the polymers, where you have the customized cabin applications shown.
Okay. That's not so good. Yeah, indeed. So we'll try to redo the.
Now something is happening. You close.
Yeah, my apologies for that. Huh?
No problem.
Yes, I tried to restart.
Okay, we see the presentation, not in presentation mode. You're on slide 5.
You see now business applications and after sales?
Perfect.
Okay.
Thank you.
Okay, so I will not repeat all of this, so you can look a little bit on the picture. So this is what we have used the parts for. Environmental footprint. So this is for the component-related parts where we are using optimized solutions. So you see here a sensor rack, left side the classical solution, and the right side an optimized solution in polymer. And this is a part which I mentioned for the tooling related stuff. So where we continue with possible new developments. So also Tim has introduced a little bit on our zero emission activity. So at the end, one topic is hydrogen application. We're using this so far. So as we are in the development. So for gas state applications, so non-cryogenic applications, so short before a fuel cell or the engine itself. Mainly for pipes, so pipes, distributors, manifolds, all this kind of things, and we're using PEC technology with carbon fiber reinforced. A second application for when we look for clean aviation is for sure still the increased efficiency, yeah? Which is on our radar, and especially here we see some applications in the ultra-high bypass ratio engines. So that means the higher the bypass ratio gets, so the more efficient the engine is. But when we are using this for conventional aircraft structures and designs, so the installation space to the below the wing, especially our pylon, is very reduced, and that means we need to find some new technologies. So in here we are looking especially for heat exchangers, which are usually also quite large.
Excuse me, Volker. It's frozen again, so it's hard to follow your explanation.
Maybe sorry, really, my apologies.
It's best to go out of presentation mode. Just leave it in the PowerPoint. That will probably work better.
Try to make it as large as I can. Yeah. Yes, and interrupt me if it happens again.
Yeah.
Okay, so for the ultra-high bypass ratio, which we're using potassium alloys as well as nickel chrome alloys, and once again, potential applications are heat exchangers as a special, I would say, a complex design for powder bed metal technology. So that was mainly it. So what are the takeaways of the and the conclusions of the presentation? So we're using a metal additive manufactured parts, flying and also non-flying parts. Right now with powder bed process on titanium as well as Inconel. And we are developing also the direct energy deposition technology with filament as well as powder. And we have implemented polymer parts with powder process, polyamide 12, and filament process with the Ultim. So we have applications in Syria and also after sales business. The environmental footprint we see mainly two aspects. So for the reduced weight on component level as well as the avoidance. Nevertheless, here to say as well, so we're not talking about a huge impact. So the I would say the amount of parts that are manufactured is still very, very low, at least on our running programs. So let's see what happens when we start a new program, and then we can really see what kind of benefit we can bring with respect to the environment. So as an outlook, we look for our hydrogen application. So where we currently use it 3D printing for our I would say gas state hydrogen for piping systems, and at the end, we want to use it as well for ultra-high bypass ratio concepts, especially for heat exchanger applications. So that was it. Many thanks for your attention, and you're more than welcome to address a few topics and questions to me.
Thank you, Volker. Looking at the questions, I will take a question from Andy van Aarschot. For PBF and DID for metals, what's the typical cost target that you look for or can achieve compared to traditional manufacturing methods?
I cannot give you such kind of figure. So we're looking here, we are comparing part to part. So at the end, this is really depending on the existing technology. So at the end, this is how we are going to do it.
Very good. Thank you very much. Unfortunately, we have run out of time. So there's no room for further questions, and for wrapping up, it will be difficult. I would like to thank Emil for bring us his insights on structural integrity, testing, design, risks and mitigation methods. Tim for his focus on cryogenic composite tanks concepts, giving an overview of the different avenues of research, and Volker for these hands-on insights on additive manufacturing at Airbus and how to introduce incurring production processes. I would like to thank the speakers for sharing with us their ideas and thoughts. And hand them a virtual present, my perpetual gratitude. To the participants, I hope you found it inspiring. If you expect more from us, just tell us. If you're content, tell your colleagues. I thank my team for the initiative and for putting this together. And all I have to do now is wishing you all a fine afternoon and an evening also, and a very relaxing weekend. See you next time. Bye.
Thanks, Josh. Thank you, everybody.
Bye.
Bye-bye.
Bye.
Thank you. Bye. Have a nice weekend.
Bye. Bye-bye.